Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 26th lecture on nonlinear control. All right, so let's get started with a video. Now, this is a video of a very small flying robot. I want you to imagine the design process for this robot. How would you pick your actuators and how would you provide power to those actuators? What about any sort of onboard computing? Any weight that you add could have a big impact on the system, and so I want to make sure I choose these elements very carefully. Another interesting aspect is control, because for my standard robot arm, a thing like a gust of wind doesn't really matter. But for this small flying craft, a gust of wind could have a big impact on the overall system. And so I'm going to be thinking about nonlinear, accurate controllers for these little robots. And that'll lead us to today's lecture on nonlinear control. And I want to apply that nonlinear control to our serial robot arms. First, I'm going to think about multivariable control laws and try to convince you that they work. In order to do this, I'm going to apply Lyapunov stability analysis to robot arms. All right, so let's get started with the block diagram we talked about in our previous lecture. Now, this is a diagram for a multivariable control law. The idea is that my robot measures its desired joint position as well as its current joint position, and both of these are inputs to my controller. The important thing is that these are vectors. I'm considering the desired position of all my joints, as well as the current position of all my different joints. Based on all of this information, my robot is going to output a vector of joint torques. So I'm telling all my different motors what they should do. And so I have one unified control law for my entire robot arm. A nice thing is that if I can find this controller, I can analyze the stability and performance of my entire robot arm, again, just looking at this one individual controller that I'm thinking about. So here's an example of one of these multivariable control laws. That's what you see right here. I've got my joint torques, and again, these are the torques that I'm commanding to all the different joints along my robot arm. If my robot arm has n joints, this will be an n by 1 vector. So here's my joint torques. And then on the right side, I've got my position error and my joint velocity. Again, these are n by 1 vectors because I'm thinking about my entire robot arm. Now, there are a few terms in this equation that I can tune. The first one is my Kp, and the second one is Kd. These are kind of like PD gains, but they're now lifted into a matrix space. So Kp will be an n by n matrix, and Kd will also be an n by n matrix. Since these are gains, they're left up to the designer, and I can tune and pick these values as I see fit, but there's one rule, and that is that both of these matrices must be positive and symmetric definite. And we'll see why as we kind of move through our analysis, but just keep that in mind that these are two symmetric and positive definite matrices. Finally, on the right side, I've got my gravity vector. Now this is an n by 1 vector that just cancels out the effect of gravity. So gravity is pulling my robot towards the ground, and these torques will just keep it in place passively. All right, so I've got this equation, and our question is this a good idea? Like, is this controller going to work? Is it stable? And will it cause my robot to converge to the desired position? Remember that with control, our whole point is I want to take my robot and move it to desired positions in space. So is this controller going to do that? Is it going to take my robot and move it to the desired position theta d? I think I can prove this, and in order to do so, I'm going to use something called Lyapunov stability analysis. Now, this is a very general technique for analyzing the stability of control systems. And what we do is we take our system and we try to find an energy function V. And we want that energy function to satisfy two conditions. First, the energy function should be positive for all values except for the equilibrium. So when x is equal to 0, I'm at my equilibrium and my energy should be 0. Everywhere else, it should be positive. The second rule is that the time derivative of energy should be either 0 or negative. And the idea is that I have energy in my system, it should be decreasing over time until I converge to my equilibrium. So again, I've got an energy function. It starts off somewhere, maybe a positive value. Energy decreases. My system converges to some sort of steady state, some equilibrium, and I've shown that this is in fact a stable system. All right, so that's the general idea. Now I need to talk a little bit about a few technical things that we can do with Lyapunov stability analysis when we apply it to these robot arms. Now, these rules are actually covered in more detail in the practice set from the previous lecture, so I encourage you to watch that lecture and go through the practice set if you haven't already. The first rule is that if A is a symmetric and positive definite matrix, then X transpose AX will be positive for all values of X not equal to 0. And then when X is 0, I've got X transpose AX is equal to 0. This is going to be nice because I mentioned that for Lyapunov stability analysis, I want these energy functions that are 0 at equilibrium and positive everywhere else. Well, I can just use this sort of construction, and I've got that condition for my energy function. Another nice thing is that if A is a symmetric positive definite matrix, then I can switch the order of multiplication. So if I had X transpose AY, that is equivalent to Y transpose AX. And the second to third step, here I'm just using the fact that A transpose is equal to A because it is a symmetric matrix. Okay, so we're talking about these symmetric positive definite matrices. Where are they coming from? Well, one of them actually is the mass matrix. So what we found in our dynamics, I mentioned it at the time, but probably didn't seem that relevant. Here's when it becomes important. So the mass matrix M is actually a symmetric and positive definite matrix. So I can use it in each of these, for either of these equations. And finally, and this one's a bit esoteric, and it comes up in one specific place in our derivation. If you take the time derivative of your mass matrix, so if you get m dot, that minus 2c, where this is the Coriolis matrix, so m dot minus 2c, it turns out that that is a skew symmetric matrix. And so if you have something like x transpose m dot minus 2cx, that is going to be equal to 0 for any value of x. Now, this is the actual, like what the actual statement is. Intuitively, if you like, you can simplify this down to something like m dot minus 2c is equal to 0. This isn't technically the case, but I think it's a nice simplification just to keep in mind. This is what you want to use. So whenever you see this m dot minus 2c, you're probably going to get some sort of cancellation in your analysis. Okay, so let's apply this Lyapunov stability analysis to our multivariable control law and see what we get. So I want to start off with just some of the main equations that we've got. So here's my controller. Again, we talked a little bit about this earlier. And here are the dynamics for my entire robot arm. If I plug in this controller into my dynamics, I get this equation. And again, just intuitively, your controller is telling you what torques you want to apply. And the dynamics are telling you the impact of those torques. Like if I were to apply these torques, this is how my system would move. So I'm just going to combine these two equations. My gravity vector cancels out, and I'm left with these closed loop dynamics. What I'd like to do is I'd like to use Lyapunov stability analysis to show that for this closed loop system, it's stable and the equilibrium is going to be 0 velocity and my robot moves to the desired position. So again, I want to show that it's stable and I have an equilibrium. The equilibrium occurs when I've got 0 velocity and my robot moves to the desired position. So my first step when I'm applying Lyapunov stability analysis is to come up with one of these energy functions. And this is probably the hardest step because, of course, there's many energy functions I could choose, and it's kind of hard to think about what would be the right one to pick. So I like to start with this by thinking about the equilibrium. So what variables do I need to have in this energy function in order to think about my equilibrium right here? And that at what value should my energy function be equal to 0? So maybe pause the video, think a little bit about just those two questions. And if you can answer those, you can probably start building up the right energy function. So I recognize that my energy function better include theta dot, and it better include something like theta and theta d, because I want to have these in order to find my equilibrium. Now, the desired equilibrium occurs when I've got 0 velocity and theta is equal to theta d. And that's what I'm reflecting in these two terms right here. This first one has got my theta dot, and it's the kinetic energy. It's the energy due to motion of my system. In a scalar space, you could think about this as 1/2 mv squared, but now because we're dealing with vectors and matrices, it becomes 1/2 my velocity, theta dot, transpose times my mass matrix times my velocity again, theta dot. So this is the kinetic energy of my robot arm, and you'll notice that this is 0 when I've got 0 velocity. So when theta dot is 0, this term is going to be equal to 0. So great, that corresponds to one element of my equilibrium. Now here's my second term over here, and this is just the potential energy due to a spring. Now you might correctly say that there is no physical spring in my system, and that's right. But I actually do have a proportional gain, and that's acting like a spring, just in control space. So again, this is the energy caused by that spring. And so it's 1/2 my error times my proportional gain times my error again. And these are all vectors and matrices. And you'll notice that this entire term is going to be 0 when theta is equal to theta d. And again, that corresponds to the second element of my equilibrium. So I've reflected the equilibrium with this energy function. Overall, the energy function will be 0 when my robot is at the equilibrium. It'll be positive everywhere else. So this satisfies the first condition I need for a valid energy function that's supporting my stability analysis. The second thing I need to do is take the time derivative of the energy function, and I want to show that this energy function is decreasing, or the energy is decreasing over time, and my system is converging to the equilibrium. So to do that, I want to look at v dot, the time derivative of my energy function. I've got two different terms here. I'm going to take the time derivative of my first term and the time derivative of my second term. Now, if you're looking at the individual elements here, remember that my joint velocity depends on time. My joint position also depends on time. And theta d is actually a constant. That is not going to depend on time. So when I'm taking these different derivatives, I'll have to think about the derivative here, here, and here. I do not need to think about the derivative specifically of theta d. So let's look at this first term because it's a bit more complicated than maybe it seems at first. So if I want to expand this out, I'm going to take my time derivative of 1/2 mv squared, essentially. I'm going to have 1/2 my acceleration times my mass matrix times my velocity, and then just the reverse of that, 1/2 my velocity times my mass matrix times my acceleration. And to get these, I'm using the chain rule. The last element of that chain rule is going to be 1/2 theta dot times my mass matrix, the time derivative of that mass matrix, so m dot times theta dot again. So maybe pause the video and kind of go through the process of deriving this if you haven't already, because it is a little bit complicated. You're using your chain rule, you're kind of expanding out each of these different terms when you take your derivative. And you might notice that we've got one equation that we can apply here, and that's that I've got this mass matrix, and that's a symmetric positive definite matrix, so I can use one of the properties of symmetric positive definite matrices. This is something like x transpose ay is equal to y transpose ax. And here's the same thing, right? This is theta double dot transpose m theta dot, and here I've got theta dot transpose m theta double dot. So I can actually just reverse the order of one of these to combine them, and so I'm left with what you see right here. So this is the time derivative of my first term, and now I want to repeat that process for the second term. So I'm going to be taking the time derivative of my second term, and I'll go through the same sort of steps. Remember again that theta d is a constant. I'm just looking at the derivative with respect to theta. I have to expand this out with my chain rule, and then I can combine some terms, and then I end up with what you see right here. So I've got negative theta dot transpose times kp times theta d minus theta. And again, I'm using this property of symmetric positive definite matrices to combine these two terms. Just switching the order of multiplication does not have an impact on the answer. Okay, so I've simplified things down, and now I've got my time derivative of my energy function. So I've got v dot, and here are all the different terms. Now, I can still simplify this a bit more, and this is where some of the beautiful math comes into play. Now remember that I've got my dynamics of my robot, and I actually found these closed loop dynamics that you see right here. I've got m theta double dot, and look, I've got m theta double dot here as well. So maybe I can plug in these closed loop dynamics and just see if something cancels out. Maybe pause the video, think about it. Hopefully you notice that, all right, I've got positive kp right here, I've got the negative kp, so these two terms will cancel out. And I'm left with a few other terms. I've got 1/2 my time derivative of my mass matrix minus my Coriolis matrix, and then here's my negative kd times theta dot. If I just distribute out the joint velocity, I end up with what you see right here. And here's where that one kind of unusual property comes into play. I've got m dot minus 2c. All right, this is going to be a skew symmetric matrix. And so this term will cancel out. And I'm left with v dot is equal to negative theta dot transpose times kd times theta dot. So we started off with this pretty large equation for our energy function. We took some derivatives. We applied back in our dynamics. After a bunch of math and manipulation of these different equations, I ended up with the following equation for my energy function's time derivative. So I know I've got a valid energy function, and now I can see that the energy is actually decreasing over time. And to understand this a little bit better, remember that KD, that is a gain matrix that we get to pick. And a good choice might be a symmetric positive definite matrix, because if I choose KD to be a symmetric positive definite matrix, then this multiplication will always be positive for no matter what value I have, except for when theta dot is equal to 0, and then a minus sign in front of that. So I'm always going to have some sort of negative value here. So my energy is going to be decreasing in my system. So that means my system is stable. And if I unwind my definitions a little bit more, I realize that the energy in my system is going to decrease until V is equal to 0. And based on the definition of the energy function, V is equal to 0 at my equilibrium. And this equilibrium occurs when I've got 0 velocity and theta is equal to theta d. So the multivariable control law that we introduced, what it's going to do is it's going to take my robot, It's going to make it go to the desired position. It's going to be stable. It's going to cause the robot to stop moving, have zero velocity, and again, come to rest at that desired position. So it's a valid way for us to control our overall robot arm to make it move where we want it to move in a stable manner. All right, so maybe a lot to take in. Perhaps you want to practice this a little bit more, but the main idea is that yes, I can use Lyapunov stability analysis to verify that multivariable control laws do work for my robot arm. If you do actually want to practice this a bit more, you can check out the practice set. You can find that in the description or in the pinned comment. Again, the first page has the questions and the following pages have their answers. Once you've worked through that, I want to do one final lecture on control. And here we're going to try to tie in everything we've covered so far and talk about how we can control a simulated robot arm. So I look forward to seeing you there.